Hello everybody, welcome into another lesson. So today we are going to talk about factoring by grouping part 2. So we get into some more difficult expressions to factor here. Take this one for instance. We have 3a plus ab plus 3c plus bc. Looking at that, you're like, how the heck am I going to factor that? Well, if we look at the first two terms, you notice they have a common a that factors out. Then if you look at the last two terms, they have a common c that factors out. So why don't we take this particular expression two terms at a time? If we take the first two terms, you can factor out an a. A times what equals 3a? Well, that'd be 3, because a times 3 equals 3a. Plus a times what equals ab? Well, that'd be b, because a times b equals ab. Alright? So we have a times a quantity of 3 plus b, plus the second two terms, we have a common c that'll factor out. C times what equals 3c? Well, that would be 3, because c times 3 is 3c. Plus c times what equals bc? Well, that'd be b. C times b equals bc. Okay? So now we have a common factor. We have two terms with a common factor of 3 plus b. We can factor out that common 3 plus b, and then you end up getting what's left is a plus c for the other factor. So in order to factor this, the proper answer you should get would be the quantity of 3 plus b times the quantity of a plus c. And I do got more examples. Alright, let's see here. We have RS plus 5R plus ST plus 5T. Alright, so we got RS plus 5R plus ST plus 5T. Well, let's look at how we're going to factor this, come up with an approach. It's kind of like the last problem, because between RS and 5R, the first two terms, you have a common R. Between the second two terms, ST and 5T, you have a common T. So let's factor out an R from the first two terms. Factor out your R. Now R times what equals RS? Well, that'd just be S, because R times S is RS, plus R times what equals 5R? Well, that'd just be 5. So you get R times the quantity of S plus 5, plus the second two terms, you have a common T that'll factor out, times, alright, T times what equals ST? Well, that'd also be S, plus T times what equals 5T? Well, that'd be 5. So now you have two terms with a common factor of S plus 5. So we'll factor out the S plus 5. And then that'll leave you with the quantity of R plus T for your second factor. So your second factor should give you, your total factor should be the quantity of S plus 5 times the quantity of R plus T. Let's get a different marker. So that's what you would get for that one. Alright. We have x squared minus 2x plus xy minus 2y. Okay, so we got x squared minus 2x plus xy minus 2y. Well, it looks like we're going to break this into groups of two terms again, because between x squared and negative 2x you have a common x. Between xy and negative 2y you have a common y. So let's start with the first two terms. Let's factor out that common x. X times what equals x squared? Well, that'd just be x. Minus x times what equals 2x? Well, that'd just be 2. So you get x times the quantity of x minus 2 plus you have xy minus 2y. Well, you have a common y you can factor out between those two terms. Y times what equals xy? Well, that'd be x minus, now you have y times what equals 2y? Well, that'd be 2. And what do you know? We have now two terms with a common x minus 2. So we can factor out that common x minus 2. That just leaves you with your second factor being the quantity of x plus y. So the complete factorization of this particular expression would be the quantity of x minus 2 times the quantity of x plus y. So it's like we're doing yesterday's work, but there's one more step involved. I didn't want to put this in yesterday's lesson because that would have been way too much. The video would have gone on just simply way too long. Here's a similar problem. We have u squared minus 2u plus uv minus 2v. Okay, so we got u squared minus 2u plus uv minus 2v. It looks like we're going to break these into groups of two terms again. So I'm not saying you're going to do that for every problem we do today, but so far that's what it's been. Alright, because between u squared and negative 2u, they have a common u, which we can factor out a common u. U times what equals u squared? Well, that'd just be u. Minus u times what equals 2u? Well, that'd just be 2. So now you have u times the quantity of u minus 2 plus, we got the second set of terms, uv minus 2v. Well, there's a common v that we'll factor out. So v times what equals uv? Well, that would just also be u. Minus, then we have v times what equals 2v? Well, that'd just be 2. So all of a sudden we have two terms with common factors of u minus 2. Now we can factor out the common u minus 2. That should just leave you left with u plus v. This was pretty much identical to the last problem we did, only different variables. But you get the quantity of u minus 2 times the quantity of u plus v whenever you factor it out. Let's see, we have h squared minus hk plus hr minus kr. Alright, so we got h squared minus hk plus hr times kr. Okay. Looks like we're going to split these into two groups of terms again, because between the first two terms, h squared and negative hk, you have a common h. So let's go ahead and factor out that common h. H times what equals h squared? Well, that'd just be h minus h times what equals hk? Well, that'd just be k. So you have h times the quantity of h minus k plus, now you got to deal with your hr minus kr. Looks like you have a common r as a factor between those. R times what equals hr? Well, that'd just be h minus r times what equals kr? Well, that'd be k. So now you have two terms with a common factor of h minus k. So let's go ahead and factor out that common h minus k. And then all you'll have left over for the other quantity would be h plus r. So the factorization for this expression should be the quantity of h minus k times the quantity of h plus r. Alright, x squared minus 2xy plus 4xz minus 8yz. Alright. So it looks like, once again, we're going to split this into the first two terms here, because if you notice, between x squared and negative 2xy, there's a common x. And if you look between 4xz and negative 8yz, there's a common, really, there's a common 2z between them. But we'll get to that in a second. Let's start with x squared minus 2xy. There's an x in common between both terms. So x times what equals x squared? That'd just be x minus, we have x times what equals 2xy? Well, that would just be 2y. So you get x times the quantity of x minus 2y plus, now we're going to deal with 4xz minus 8yz. Well, between 4 and 8, there's a common 4, that's for sure. There is a common 4. But between xz and yz, if you look at your variables, there's a common z. So really, you could factor out 4z entirely. Now, 4z times what equals 4xz? Well, that'd just be x minus, we have 4z times what equals 8yz? That'd just be 2y. So all of a sudden now we have two terms with two common factors of x minus 2y. So let's go ahead and factor out our x minus 2y. That's fine. That would just leave you, for your second quantity, you'll just get x plus 4z. So the answer you should get for your factorization would be the quantity of x minus 2y times the quantity of x plus 4z. Alright, we have p to the third minus 2p squared plus 4p minus 8. Alright, well, we need to factor this expression here. I'm going to still say we split this into two sets of two terms. It's looking that way. Between p cubed and p squared, you have a common p squared. So then p squared times what equals p cubed? That'd be p minus, and then you have p squared times what equals 2p squared? That'd just be 2. So far you got p squared times p minus 2. Plus, now we'll deal with the second two terms. Between 4p and 8, you can factor out a common 4. Now, 4 times what equals 4p? Well, simply p minus 4 times what equals 8? That'd be 2. So now you got two terms with two common factors of p minus 2. Let's factor out the p minus 2. Alright, so all you're going to have left is the quantity of p squared plus 4. Well, this is the sum of two squares. If we had the difference of two squares, we could factor a step further. But we're not doing that till we get to Algebra 2 and talk about imaginary and complex numbers. So for now, this answer would suffice, of the quantity of p minus 2 times the quantity of p squared plus 4. Because p squared plus 4 does not factor any further in the real numbers. It does in other numbers, but not in the real numbers, and we're only sticking to real numbers here in Algebra 1. Alright. We have 3a to the third plus a to the second plus 6a plus 2. Alright. So 3a to the third plus a to the second plus 6a plus 2. Well, looks like we're going to break these into two groups of two terms again. Between 3a to the third plus a to the second, what do they have in common? They have an a to the second in common. So a to the second times what equals 3a to the third? Well, that'd just be 3a. Plus, now a to the second times what equals a to the second? That'd just be 1. Alright, so we've gotten a to the second times a quantity of 3a plus 1 so far. Plus, let's look between 6a and 2. Between 6a and 2, what's the common factor? Definitely a 2. So, 2 times what equals 6a? Well, that'd be 3a. Plus 2 times what equals 2? Well, that'd just simply be 1. Now we have two terms that have a squared, that rather have 3a plus 1 as your common factor. So go ahead, factor out your common 3a plus 1. That's going to leave you with the quantity of a squared plus 2 left over. And in the real numbers, we can't factor a squared plus 2 any further. So your factorization will be the quantity of 3a plus 1 times the quantity of a squared plus 2. Alright, let's see. P squared minus 2pq plus PR minus 2QR. So we've gotten P squared minus 2pq plus PR minus 2QR. How do we factor that? I think once again I'm going to recommend that we do the set of two terms approach, two sets of two terms. So let's just start with the first two terms. Between p to the second and then negative 2pq, what do they have in common? They have a common p. So factor the p out. P times what equals p to the second? That'd just be p minus p times what equals 2pq. That'd just be 2q. So so far you got p times the quantity of p minus 2q plus, let's deal only with the second two terms now. You got pr minus 2qr. Between those two terms, what do they have in common? They have an r. So then factor out your r times what equals pr? That would just be p minus, we have r times what equals 2qr? That'd be 2q. Now we have two terms that have a common p minus 2q. So we can factor out the p minus 2q. That's just going to leave you left with p plus r for your second factor. So the factorization of this should be the quantity of p minus 2q times the quantity of p plus r. Alright, let's see. U squared minus 3uv minus 6uw plus 18vw. Alright, so we got this mess here. We have u to the second minus 3uv minus 6uw plus 18vw. It looks like, once again, we want to take the separating it by two sets of two terms approach. So let's go ahead and do that. You'll end up getting, you factor out u squared and 3uv, what's the common factor? Definitely a u. So factor out your u. U times what equals u to the second? That'd be u. Minus u times what equals 3uv? Well, that'd be 3v. So far we have u times the quantity of u minus 3v. Now let's look at the second two terms, negative 6uw and positive 18vw. We can certainly factor out that negative 6, but between between the variables uw and vw, there's a common w. So we can really factor out negative 6w. So now negative 6w times what equals negative 6uw? That'd just be positive u. Now, negative 6w times what equals positive 18vw? That'd be negative 3v. Because if you take this, negative 6w times u, you get negative 6uw. And then take your negative 6w times the negative 3v, you get positive 18vw. So we now have two terms with the same common factor of u minus 3v. So let's factor out your u minus 3v from each of those. What you have left is u minus 6w for your other factor. So the factorization would be the quantity of u minus 3v times the quantity of u minus 6w. Make sure you all can see. Looks like you can. Alright. I have about 8 more. I have, let's see, 3hk minus 2k minus 12h plus 8. So I got the quantity, the expression of 3hk minus 2k minus 12h plus 8. Well, I think we're going to group this into two sets of two terms again. Let's look at the 3hk minus 2k. What do those two terms have in common? Definitely a k. They have a k in common. So k times what equals 3hk? Well, that'd be 3h minus k times what equals 2k? Well, that'd just be 2. So far you have the quantity of k times 3h minus 2. Now, between the second two terms, negative 12h and positive 8, what's the greatest common factor? That'd be negative 4. So you'd have minus 4. So negative 4 times what equals negative 12h? That'd be positive 3h. Then negative 4 times what equals positive 8? That'd be negative 2. So now you have two terms where you have a common 3h minus 2. Let's go ahead and factor that out. Factor out your 3h minus 2. That just leaves you with k minus 4 for your second factor. So the factorization of this would be 3h minus 2 times the quantity of k minus 4. Alright. We got 3ab minus b minus 4 plus 12a. So if you want, what you can do is you can switch the 12a and negative 4 around by the commutative property. So let's go ahead and do that. You'll get 3ab minus b plus 12a minus 4 if we use the commutative property and switch those around, the last two terms. Now that we've done so, it looks like we're going to do the two sets of two terms approach again. So between 3ab and negative b, what's the common factor? Well, definitely b. So then factor out the b. B times what equals 3ab? Well, that'd just be 3a. Minus b times what equals b? Well, that'd be 1. So far we have b times the quantity of 3a minus 1. Plus, we'll deal with the second set of deal with the second set of terms. Between 12a and 4, what's the common factor? Definitely 4. Alright, factor out your 4. 4 times what equals 12a? Well, that'd be 3a. Minus 4 times what equals 4? That'd just be 1. So now you have two terms with a common 3a minus 1. So all you gotta do now, factor out your 3a minus 1. And then you'll just have the quantity of b plus 4 left. So the factorization of this would be the quantity of 3a minus 1 times the quantity of b plus 4. Alright, let's see. 4z to the third minus 6z to the second minus 6z plus 9. So we got 4z to the third minus 6z to the second minus 6z plus 9. I think we're going to take the approach of split them into two sets of two terms again. So let's start with the first two terms. Between 4 and 6, just focus on the coefficient for a minute. Between 4 and 6, what's the greatest common factor? Definitely 2. Now between z to the third and z to the second, what's the greatest common factor? That'd definitely be z to the second. So you factored out a 2z to the second. Alright, so 2z to the second times what equals 4z to the third? That'd be 2z. minus, you have 2z to the second times what equals 6z to the second? Well, that'd just be 3. Okay? Now, let's look at the second two terms. Between negative 6z and positive 9, what's the greatest common factor? We can do a negative 3. Negative 3 is definitely the greatest common factor. Now, negative 3 times what equals negative 6z? That'd be positive 2z. Now, negative 3 times what equals positive 9? Well, that'd be negative 3. So all of a sudden, we have two terms that have identical factors of 2z minus 3. Let's go ahead and factor them. Factor out your 2z minus 3, you're simply left with the quantity of 2z squared minus 3 for your second factor. Now, we do have the difference of squares. However, since they're not perfect squares, we aren't going to factor them because it's really not pretty. It's honestly not a pretty factorization. It involves a bunch of square roots and stuff, which I don't think anybody really wants to see right now. So since they're not perfect squares for the second two terms of the second factor, I would just let it go. I would just leave it the way it is. Alright, 5 more rather, sorry. 5 more. We have 3u to the third minus u to the second minus 9u plus 3. Alright. So 3u to the third minus u to the second minus 9u plus 3. Looks like we're going to pull the two sets of two terms approach again. So look at 3u to the third and then u to the second. What's the greatest common factor? Definitely the u to the second. So factor out the u to the second. U to the second times what equals 3u to the third? That'd be 3u. Minus u to the second times what equals u to the second? That'd just be 1. So far we have u to the second times a quantity of 3u minus 1. Now, between negative 9u and 3, what's the greatest common factor? I'm going to say a negative 3. Let's factor out a negative 3. Negative 3 times what equals negative 9u? That'd be positive 3u. Now, negative 3 times what equals positive 3? That'd be negative 1. So now we have two terms with the common factor of 3u minus 1. So let us go ahead and factor out the 3u minus 1. That would leave you for your second factor of u to the second minus 3. And honestly, u to the second minus 3, we could factor that because it's in the set of real numbers. If we did, since the second number is not a perfect square, you can leave it this way, at least in Algebra 1. In Algebra 2, you'd have to factor it more. But if you were to factor that further, you would get the quantity of 3u minus 1. Now, factoring the difference of two squares, you take the square root of the first number plus the square root of the second number. Well, the square root of 3 is just that. Then you take that times the quantity of the square root of the first number minus the square root of the second number. So if we were to factor it further, you would get the quantity of 3u minus 1 times the quantity of u plus the square root of 3 times the quantity of u minus the square root of 3. That would be the complete factorization. But for now in Algebra 1, we can, if it's not a perfect square on both terms, we can simply leave it. We can write 3u minus 1, that quantity, times u squared minus 3. That would be acceptable. Either of these two answers would be acceptable in Algebra 1. Actually, later in Algebra 1, we'll be dealing with more square root equations, so even then we'll factor those. Alright, 4 more. We have the quantity of h squared k squared plus 4k squared. That quantity plus we have h squared k plus 4k. Alright, they kind of already separate it into two groups of two terms for us. So what we're going to have here, do the first two terms, between h squared k squared and 4k squared, what's a common factor? Definitely going to be k squared. Now factor out your k squared times what equals h squared k squared? That would just be h squared plus k squared times what equals 4k squared? That would just be 4. So far you have k squared times the quantity of h squared plus 4. Plus, let's look at the second two terms. Between h squared k and 4k, what's a common factor? Just simply k. Factor out your k times what equals h squared k? Well, that'd just be h squared plus k times what equals 4k? Well, that'd just be 4. So now you have two terms with a common h squared plus 4. Let's go ahead and factor that out. Okay, that just leaves you with your quantity of k squared plus k left over. Alright, couple things. One, first factor is the sum of two squares. We can't factor that in the set of real numbers, which is all we're working with in Algebra 1. So the h squared plus 4 can stay. However, the k squared plus k, we could definitely factor that a step further, could we not? If you factor out a common k, so you'll have h squared plus 4, then you'll factor out that common k times what equals k squared? That'd just be k plus k times what equals k? That'd just be 1. So really your complete factorization, we're going to switch these around by the commutative property of multiplication and get the same result. You would get k times the quantity of k plus 1 times the quantity of h squared plus 4. So your complete factorization is going to be k times the quantity of k plus 1 times the quantity of h squared plus 4. Alright, 3 more, then we're done. So we got a squared b squared plus, we got that quantity plus, I'm doing it wrong, forgive me. I'm writing it wrong. We have a squared b squared plus 2a squared. That quantity minus 2ab squared plus 4a. Alright. So they already break it into the two terms approach for you, the two sets of two terms. So the greatest common factor between a squared, b squared, and 2a squared is definitely a squared. So you're going to factor out your common a squared. Now, a squared times what equals a squared, b squared? Just b squared. So a squared times b squared equals a squared, b squared. Plus, you have a squared times what equals 2a squared? Well, that'd just be 2. So far you have a squared times the quantity of b squared plus 2 minus between 2a b squared and 4a, what's a common factor? That'd just be 2a. So you factor out your common 2a. In order to get 2ab squared, 2a times what equals 2ab squared? Well, that'd just be b squared. Now, 2a times what equals 4a? Well, that'd just be 2. So what do you know? You got two terms with a common factor b squared plus 2. So factor out your b squared plus 2. That leaves you with a quantity of a squared minus 2a left over. Well, b squared plus 2 is the sum of two squares. We can't do anything with that in a set of real numbers, so we're good there. But the a squared minus 2a, we could definitely factor further. If you keep your quantity of b squared plus 2, now take your second factor, you factor out a common a times what equals a squared? That'd just be a minus a times what equals 2a? That'd be 2. So really, we're going to use the commutative property of multiplication to rewrite this. You would get a times the quantity of a minus 2 times the quantity of b squared plus 2. So, yes, the quantity you get for the factorization is a times the quantity of a minus 2 times the quantity of b squared plus 2. And that's all the further we can go for factoring those. Two more, then we're done. Alright, let's see. We have x cubed minus 3x squared minus x plus 3. So we got, let's see, x cubed minus 3x squared minus x plus 3. Looks like we're going to do the two sets of two terms approach. So between x cubed and 3x squared, what's the common factor? Definitely x squared. X squared is factored out as a common factor of the first two terms. X squared times what equals x cubed? Well, that'd just be x minus x squared times what equals 3x squared? That'd just be 3. So far we have x squared times x minus 3. Now we got the second two terms, the negative x plus 3. We could factor out a negative 1. Factor out your negative 1 times the negative 1 times what equals negative x? That'd be positive x. Now negative 1 times what equals positive 3? That'd be negative 3. So all of a sudden you have two terms with two identical factors of x minus 3. Let's go ahead and factor out that x minus 3. What you're left with is the quantity of x squared minus 1 for your second factor. Well, x minus 3 doesn't factor any further. That's as good as it's going to get. But x squared minus 1, that's the difference of two perfect squares. We can factor that further. If you do that, you'll get x minus 3 times the quantity of x plus 1 times the quantity of x minus 1. So the complete factorization of this expression would be the quantity of x minus 3 times the quantity of x plus 1 times the quantity of x minus 1. And I have one more. Then we're done for the day. I think we're in for definitely a 3-part lesson. Yeah, we're definitely in for a 3-part lesson for sure. Because this factoring by grouping can get pretty intense. So I would rather teach it right. I would rather take the time and teach it because there are a lot of components to this. This is part 2 out of probably 3. Okay. So last problem here, we got n to the third plus 2n to the second minus 4n minus 8. Well, separate them by the 2 terms again. We'll do n to the third plus 2n to the second. We'll focus on those 2 terms first. What's the common factor? Definitely n to the second. Factor out your n to the second. N to the second times what equals n to the third? That'd just be n. Plus, we got n to the second times what equals 2n to the second? Well, that'd just be 2. So far you have n to the second times the quantity of n plus 2. Alright, now between negative 4n and negative 8, what's the greatest common factor? Definitely negative 4. We could factor out a negative 4. Negative 4 times what equals negative 4n? Well, that'd just be n. Then negative 4 times what equals negative 8? That'd be positive 2. So what do you know? We got 2 terms that have the common factor of n plus 2. Let's go ahead and factor out the n plus 2. That would just leave you with a quantity of n squared minus 4 left over. Well, the n plus 2 doesn't factor any further. However, n squared minus 4 does factor further. It's the difference of 2 perfect squares. If you do this, you'll get n plus 2 times the quantity. Then you'll have this, let's see, the factorization of n squared minus 4 is also n plus 2 times n minus 2. Notice the n plus 2 occurs twice. You're multiplying it by itself twice. You can actually write this as n plus 2, that quantity to the second power, times the quantity of n minus 2. So the factorization of this would be the quantity of n plus 2 to the second power times the quantity of n minus 2 to the first power. So that's it for factoring by grouping part 2. Next lesson will be factoring by grouping part 3. We'll get into some even harder equations. So I hope everybody has a good night. Take care.